Okay, we're going to do the last problem in chapter 5. And once we're done with this problem, we're ready for the first midterm. So that's the bad news. The good news is this is sort of a penultimate problem. And if you can, that word didn't quite apply. This is an ultimate problem. If you can do this problem, you can do anything. If you can do this, understand it, you are in great shape. So what I have here is this is like a fence post. So it's a rectangular post here, and around the post somebody's put a collar, all right? And the fence post is smooth and square here at the cross section. So the fact that it's smooth, it means that this post provides absolutely no support to this collar. This collar is free to slide up and down at will. Okay? Now, out of this collar, somebody has welded a pipe. That's what we're seeing here. And it comes out 12 feet for whatever reason. And when you get out 12 feet at this point D, there's 45 pounds hanging straight down. And when you get to D, if you're coming out, there's this left turn notice the axis here, right here. This is the y-axis. So this is a turn. It's going out in the x, and we have a turn into the y. And it's 4 feet long. And when you go out 4 feet, then at the back here, there's a cable connected at B, and that goes back to a wall here at C. All right, so let's see what we can see about that. If you went through the center of this thing, here's the center of the collar coming off, that would continue along. That's where this coordinate system is. So we have x coming out this way, going through the center of the collar is y, going up here is z. All right, so if you go over 8 feet and then up 6 feet, then pinned into a wall is this cable. All right, so what do we have? The cable will be a two-force member, so the force is going to go along from B to C and back and forth into here. And you got a force here. And so what we want to do is find what is the tension in that cable and what are the reactions of the fence post, which is frictionless, on this collar. All right, so you have these sides of the post. The sides will push against the sides of the collar. And likewise, if you think about it, okay, picture if you could put your hand here and kind of lift and stuff. If I was to lift this up, it would force this top edge to push against the fence post and the bottom edge back here to push against this back edge of the fence post. So as various parts of the fence post come in contact with this collar, okay, so if I try to twist this way, then the fence post could, let me go to a pencil here, could push back this way, and the back side push back that way. See, I have one going that way, one going that. Well, that'd be a couple moment. So we can have moments. We can have, just from the contact of the side, the face of the collar against the face of the face post, we can have forces by the face post and the collar. We can also have torques. Now, so we have a face here, we have a face there. All right, so this face can push against the collar, that face can, and likewise the respective other side of each of these. So that would be, if we look at this, we could have, if something pushed against here, that would be a force in the y. If something pushed against there, that would be a force in the x. So we can have forces in the x and the y. But note, we cannot have a force by the fence post in the z because there is no friction. This thing is free to slide up and down. All right? So the reactions to the fence post are, we'll have to solve for this, but they can be in the x and the y direction. So allow me to do the following drawings, add to the drawing here, to try and do another free body diagram. This is a little complicated to draw, so allow me to break protocol, and I'm just going to use the original drawing as my free body diagram, as it were. So clearly, I have tension going on this way. All right, so just picture I cut this off and I put in a tension in here, which this thing's calling BC, so I'll call this FBC. All right, no problem. All right, so I'm going to have, this is going along the Y direction. I'm going to use my pen. And clean that up a bit. So this would be, let's see what we have here, FA. So I'm just going to call this, let me just call this AY. Okay. And then coming along this in the back, and I'm taking this in the positive X direction, this would be AX. I'm really referring to FA here. All right. So I can have a force in the X, I can have a force in the Y. And depending on which face is in contact with the collar, it's possible this actually points back and then this points back or whatever. I'm going to assume these are in the positive X and Y direction, and if I'm wrong, I'll get negatives for these and the signs will all work out. So it'll tell me how to write it very easily. All right, so in my free body diagram, I put the tension in, so I'll slash that off. I put FA. What about MA? What are the moments this thing can do? Well, this thing can exert moments in all three axes, actually. It's kind of wild. So, here, what I want to imagine if you come here and grab this 4-foot thing with your hand and you shook it up and down. All right? That would make this thing go like this. Or that would be rotating about the y-axis. When I shake this, grab this piece here and shake up and down, I'm rotating about the y-axis. So I'll just put another line in the y-axis, and I'll call that M-A-Y. So as I can see, I have freedom to move that way. Okay, now I want to take this again, and instead of going up and down, I want to go like this with it. Okay, see my fingers what I'm doing? I'm going to twist this bar. See, I can twist that. I could grab that and I can twist. Okay, well, twisting would be twisting around the x-axis. Picture, there's the x, twist. So I'll go over here and go, okay, I can have that too. That's some torque about the x-axis that this thing could put on that. Now, how would it do that? If I twisted it, then you would have this back surface and that surface right there as they clank in against, or up top and then the bottom one on the other side. As they clank the surface, that would exert a counter torque. Okay, so I'm just going to assume these are in the positive direction and let the signs correct it all. If they're going the other direction, I'll get a negative. Don't care. Now the z-axis goes up, so that would correspond to here, twisting, maybe if I go from the top, like this. Picture twisting the fence post. So how would I do that? Well, picture grabbing the base here and going side to side. All right, that would do a twisting on the fence post. So I'll take that in the positive z direction too. M-A-Z. So I've got all the reactions of what can happen at the collar. 2 forces, 3 moments, and then I have a force here at D, which I don't need to redraw, and then I have this one tension going up here. All right. Now I know this is going straight down, minus 45Z. That's easy to handle. My next problem, to start setting this problem up, is I need the orientation of this force. It's going from B to C. I need that orientation. Well, so the easiest way to do that is just to, let's start with a vector. I'll call VBC. And what does that do? Well, it goes, here's that 12, there's X. So I'm going to go minus 12 in the X. All right. And if I did that, that's 4 feet, and this is 8 feet out to here. So that says now go 4 feet this way in the Y, plus 4Y. and then up 6 in the z, plus 6z. So that is the direction vector. All right. Now, this is going to be a tension, so I'm going to what I want to do now is I want to get a unit vector, direction vector. And so if I was to take 12 squared plus 4 squared plus 6 squared square root, that would actually give me 14. All right, so this will be 1 on 14 minus 12x plus 4y plus 6z. All right, so what does our tension vector look like? FBC will be whatever the magnitude of FBC is. We haven't figured that one out yet. Over 14 minus 12x plus 4y plus 6z. Okay? Now we're ready to start working. So let's, if you look at this thing, what's going to be true? The sum of all the forces must be 0 in every direction. So let's see what I have. I've got, if I look over here at this collar, there's no force in the z because this is smooth. It can't exert a vertical force because there's no friction there. So I got 45 down here, and I got some aspect of tension going up there. Hey, that means I can just isolate these two, sum the forces in the z. So I'm just putting a z in there right now. And so I have a minus 45. Okay. And then I can take the z component of this thing plus the magnitude of FBC on 14 times 6. Just taking the z component. All right. One equation, one unknown. Solve. The magnitude of FBC is 105 pounds. All right. So now we know that's, so we have FBC. To sticking this up here, I have 105 over 14. If I stick all that in, if I put 105 in here, that works out to be minus 90x plus 30y plus 45z. And that's all in pounds. So I have FBC vector right here. And so that's all done. We needed to do tension, we did. Okay? Now that we have FBC, and we know this force, we can just sum forces in the x and the y, and bam, we're going to get those. So let's see. Summing forces in the x. That'll be 0. I took AX to be positive. Alrighty. This has no x component. This has a minus 90. Setting that equal to 0, we get AX equals 90 pounds. Summing forces in the y must equal 0. I took AY to be positive. We'll see if that works. This has no y component. That has a plus 30. Solve for AY. AY equals minus 30 pounds. No problem. So now FA we needed here, it's done. FA vector is 90x minus 30y pounds. All done. So we knocked that off. All that's left is we need the moments at A. We need to figure out what the fence post is doing. So it's exerting a moment. So here's what I propose to do. I'm going to sum the moments at A. So these forces don't exert a moment. That just wipes out a little work. But I still have the various twisting moments that can be occurring at A. So let's see, make sure we have space here. So sum of the moments at A, which must be 0, because we know we have static equilibrium. So I'll just stick in what the collar can do by having the edges of the collar contact the fence post. Or rather what the reaction of the fence post on the collar. So we have a max x plus may y plus maz z. We're going to solve for those. All right. Now I just need to go r cross f. So this is 12x plus 12x cross minus 45z. Okay. And now I have to do what's happening at b. So let me just go down a line. Plus, so I got to go 12x plus 4y cross, now we have FBC, minus 90x plus 30y plus 45z, bracket. All right, so these are just additive. So we're going to go x cross a y, x cross z will give us a y, and then we have all of these cross products to do. I'm going to let you do that. Okay, I'm not going to go through and do all that math. It's practice for you. But here's what you're going to find out if you do it correctly. You're going to wind up with an max plus 180x plus an may plus 0y and plus maz plus 720. All right? And what does this tell you? Well, you don't need anything in the y, and solving for these, we would get, moment about a, solving for this. This is plus 180, that means that's minus 180. Minus 180x plus 0y, minus, this is also positive here, minus 720z, and the units we were dealing with are pounds, so foot pounds. All done. So this is a problem where it looked a little crazy, but what we needed to do this problem is, in general, take the time to do a free body diagram. In this case, we just add the free body diagram to the existing picture. All right. But what you need to be able to do is visualize. And how did we visualize? Let's just bring this down a little. What's happening in the string, rope, cable? That's easy. That is just what it is. But what we had to do here was grab this thing and say, well, can I move it in the x? Can I move it in the y? How does it move in the z? That took care of the forces. And then we grabbed this thing and we twisted it in all three axes to just say, oh, wow, this fence post can exert a moment in the x, a moment in the y, a moment in the z. So that gave us all the reactions of the fence post and the collar. Then we had our other forces. And once you're there, it's just a matter of looking at the quote-unquote free body diagram, getting a strategy. In this case, it made sense because this had no z force. We could actually equate the z's. That told us what the force was. After that, then it was very logical. Sum the moments, wiped out the math from these, and bam, just a little bit of algebra, and again, it all comes clean. That's the end of chapter 5. We're going to, my next video is going to discuss what to expect on the first midterm exam. I'll catch you soon.